Okay, so we've got the technical jargon out of the way. Let's look at a specific example. Let's say that we own an ice cream shop. We're interested in understanding this relationship between the temperature outside for a given day and our ice cream sales. So what we've done here is we've gone back through our records. We've randomly selected 11 days and recorded the sales for those days. We then did an internet search and found the high temperature outside for each of those days. And we've constructed a limited sample here of 11 observations. What we're interested in here is we're going to calculate some basic statistic first, and then we'll move into some more advanced statistics to understand the relationship between the two. So the first thing that we're interested in is just the count. Now, the count in and of itself is not all that interesting, but it helps us do some things later on. So we just calculate the count using the count function. And notice that the single argument for the count here is the range of values that it's going to literally count. If you remember back from earlier on in our discussions of functions in one of the first lessons in this video series, we talked about how the count function just counts numbers. That's certainly the case. So if we had letters or text in our block of observations here, we would want to use something like the count A function. Okay, so the first statistical test that really gives us some information about the population is the average. So when we take the average, we're really trying to find the most typical observation here in our set, or the mean observation, if you will. And the average here is an estimate of the population average. So what I mean by that is that when I take the average of a sample, which I have in this case, using the average function, notice that the range for the average function here is just the range of values that we're interested in calculating the average of. When I take the average of a sample, it's the true average of the sample, but it's not necessarily the true average of the population. It's just an estimate of the average of the population. The true average for the population is going to be somewhere close to that probably if I have a good sample, but it's not going to be exactly 69.27. But it might be close enough that that gives me some information that I'm interested in. This tells me what the typical observation is for my population, or at least it's an estimate of that. And notice I have an estimate of that for temperature outside and sales. Standard deviation here tells me how much variability or how much diversity is there in my set of values. So if all of these values were the same, if I had 75 as my outside temperature for each of the days in my sample, then my standard deviation would be 0 because there's no variability across these measures. But if you look at this, I've got a pretty good range here. I've got a high temperature of 102, and it looks like my low temperature is 50. So I've got a range here of about 51 or 52. I guess it's not about, it's exactly 52. My standard deviation tells me, on average, how far away from the mean are my observations. So on average, each of my observations is about 17 degrees off of the mean. Now the interesting thing about the standard deviation calculation in Excel is there's a couple of different ways to do it. Actually, there's several. There's a few legacy ways to do it, but you've got the stdev.s function, and you've got the stdev.p function. This function, the .s function, is used whenever I'm calculating the standard deviation of a sample. And since this is a sample of temperatures, then I use this stdev.s function. If I had the entire population, so if I had every single day that I've been open for business, and all of the temperatures for those days, then that would be my population, and I would use the stdev.p function to calculate the standard deviation for that. So I have my standard deviation for my temperature and my standard deviation for my sales. Again, this is an estimate of what the standard deviation for the population would be, because I don't have the entire population here. I'm just making estimates from my sample data. Which leads us, I think, to our first piece of information that's probably new to most of you, and that's this notion of a confidence interval. So because I'm making estimates of my true average, for example, temperature for my population or for my set of days that I'm interested in, I'm not actually able to calculate the true average. The problem with that is that when I go to then use this information to make forecasts or to make other decisions later on in my spreadsheet model, I don't have any way of knowing whether this 69.27 by itself is a good estimate, and I have no way of knowing just how close to the true average we actually are with our sample average. Confidence interval helps with that, because the idea behind a confidence interval is we can use statistics based on things like the count and the standard deviation, how much variability there is in the data, to figure out a range of values within which the true average is likely to fall. So I'll show you the calculation first, then we'll talk about the interpretation of it. So to calculate a confidence interval, we use the confidence.norm function. Confidence.norm has 3 arguments. The first is alpha. That's a measure of how accurate or how confident we want to be with our result. So it's really 1 minus our confidence level. Our confidence level is how confident we want to be with the range that we put out. So if we want to be 95% confident the range that we calculate has the true mean in it, then our alpha will be 1 minus that, or 0.05. If we want to be 90% confident that the range that we calculate has the true average in it, then we would say the alpha would be 1 minus 0.9, or 0.1. Most cases we're going to set alpha to be somewhere between 0.1 or 0.01, depending on how confident we need to be in our estimation. Of course, the more confident we are in our estimation, the wider that range is going to be, and that's just a matter of the mathematics behind a confidence interval. Standard deviation we calculate above, and then size we also calculate above. So this number 10.14 tells us that how far we need to go away from the mean on both sides in order to construct an interval that we're 95% confident that the true average temperature will fall between. So to calculate our upper estimate here, we just take our average temperature, which is an E3, we add our confidence interval to that, which is an E6, and then to get our lower estimate, we take that average calculation, which is an E3, and we subtract our confidence interval from it. And we get a nice range here between 59 degrees and 79 degrees, within which we would say, we're 95% confident that the true average temperature for the population falls between those two values. And notice that our estimate is right in the middle of that particular confidence interval. That's just how the math works out. If we had a larger sample, then our confidence interval would go down, and I'll just demonstrate that. Let's say we had 150 days instead of just 11. Notice that our confidence interval goes way down, and our confidence range here goes from 66 degrees to 72. So you can see how sample size plays into the calculation for a confidence interval. Standard deviation does as well. So if we had a standard deviation of 5 instead of 17, notice that our confidence interval also goes way down. So you can see that the variability in our sample and the size of our sample has a lot to say with how big our confidence interval ends up. We've calculated the same thing for sales. So we've got a confidence interval here of 725, which means that we believe that the true mean average, or true average for sales across our population of days, is going to lie somewhere between $5,900 and $4,400, and we can say that with 95% confidence. So the idea is we're using a sample here to construct an estimate of the population. Now, if we were to use this information, let's say temperature was really important to us as we constructed a model to figure out how many people to staff in our store, or maybe even the types of flavors that we want to offer our customers, if we're thinking really kind of bizarrely here. The point is, we want a good estimate of what the temperature is likely to be, and we can use our confidence interval then to have a most likely case. That would be our average, that's our expectation, but then we would have like a best case scenario and a worst case scenario based on our lower and upper estimates, depending on how our model's set up. We'll have an example of how to do that here in just a minute.